Hey guys, so in this video we're going to talk about induction proofs with series, and more specifically we're going to go through the 6 main things you should keep in mind before tackling any induction proofs exercises which involve series, more specifically to the ones that involve series, despite the fact that you can apply great majority of these key points in any induction proofs exercises, but more specifically for series, these are key. Okay, so we're going to go through steps 1 to 6. In order to do so, we're going to use a medium to hard level induction proof exercise, which, as I mentioned, involves series. So let's get to it. So we're going to use mathematical induction to prove that the sum of the first n cubes, this is the sum of the first n cubes, is equal to n times n plus 1 over 2 squared. And this is the first thing that I wanted to mention, which is number 1, you want to rewrite your sums. Don't leave it like this. When you're writing p of n, which is the propositional function, you want to rewrite it removing this sum notation. So number 1, rewrite your sums. So our p of n is 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed. This is equal, or it should be equal. We're going to prove that this is equal to n plus 1 divided by 2, everything squared. And right now I'm going to give you tip number 2, which is there are 5 steps in any induction proofs, not just the ones that involve series, but any induction proof. So write the 5 steps. Make it clear for you and to the examiner that you're doing all of these 5 things one after the other. Step number 1 is to write your propositional function. Step number 2 is proving the base case. And in this case, given that we're talking about all positive integers, the base case is the propositional function when n is equal to 1. Now, what is the left-hand side equal to? The left-hand side is equal to 1 cubed, which is just 1. And to evaluate the right-hand side, you need to substitute 1 into this expression. And right now we have 1 times 2 over 2, which is, and squared, of course, which is equal to 1. Given that the right-hand side and the left-hand side, they're equal to each other, therefore, base case holds. Your inductive hypothesis, which is pretty much p of n, but substituting n by k. You cannot do this in your notebook, but I can, so let me just do it, which is to copy and paste. And when I copy and paste, I'm counting 1, 2, 3, 4 n's that I need to replace by k. Is that it? Well, almost. We're just missing one statement that we need to write, which is assume this is true for some positive integer k. So there you go. I am rearranging the canvas here so I can write step number 4 in any induction proofs exercise. And I know I didn't give you all 6 tips, but I'm getting there. Step number 4 is to write the inductive step, which means that you're going one iteration more after your last one, which in this case looks like this. You have this extra k plus 1 cubed here, which means that we're going to need to prove that this is equal to k plus 1, k plus 1 plus 1, and right now I'm substituting k plus 1 over here and over here, and this of course can be rewritten as k plus 2, everything divided by 2 and squared. Right now I can talk about tip number 3, which is the easy marks, or which are the easy marks. All of these marks that I got until this point, these were easy marks. You should never ever lose or waste easy marks. There's no excuse for that. The sophisticated portion of an induction proof comes right now in the inductive step, which is actually a good place to say or to mention tip number 4, which is don't freak out. Don't freak out. There's a process here. Just go through the process and you'll be fine. What is the process of solving an induction proof which involves a series? The process is the following. You're going to start with the left-hand side of p of k plus 1. So you're going to write, starting from the left-hand side of p of k plus 1, and you're going to replace what you know is true, which is p of k. You're assuming that p of k is true. Therefore, 1 cubed plus 2 cubed plus 3 cubed, all of these, all the way up to k cubed, that sum is equal to k times k plus 1 over 2 squared. And the goal is that by manipulating this and adding k plus 1 cubed obviously to it, you get to the right hand side of p of k plus 1. So this is the goal. And how do we get to the goal? Well, actually, before we do so, let me give you tip number 5. Do not expand anything. You're better off with all of your factors there. It's much easier and better to simplify like that if you try, then compared to trying to expand the whole thing. That's going to be a disaster. Keep things factored. Keep these factors there. Let me show you why. We know for a fact, because this is our assumption, that the first portion of the series is equal to k plus 1 divided by 2 squared. And then we need to add k plus 1 cubed to it. Now, of course, we can rewrite this as k squared, k plus 1 squared divided by 4 plus k plus 1 cubed, which, if we put 4 as a common denominator, we get k squared, k plus 1 squared plus 4, k plus 1 cubed. Notice that we have k plus 1 squared over here. Let me move this down a bit, over here as well. Provided that we can write k plus 1 cubed as k plus 1 squared times k plus 1. So let's actually do that first. I'm going to write this as k plus 1 squared times k plus 1, which is, of course, the same thing as k plus 1 cubed. And there we have it, our k plus 1 squared over here. Now, knowing that k plus 1 squared is a common factor, what we have is, and by the way, what does it mean to have a common factor? It is a factor that shows up in both portions, and also when you're factoring it out, it's just like you're erasing it from both of these terms. Therefore, what we have on the right hand side is k plus 1 squared, which was already written, k squared plus 4 k plus 1. Notice how we already have this guy squared, as we should, because the answer or the goal is to get here k plus 1 squared, k plus 2 squared, all divided by 4. This is the same thing that's showing on the left over here. So we already nailed one of them. What's missing is factoring this k squared plus 4k plus 4, which is showing right here, is the same as k plus 2 squared. We already have the 4. Actually, we had the 4 for a long time now, and we just finished our induction proof. This is indeed equal to k plus 1, k plus 2 squared divided by 2 first and then squared. And this is equal to the right hand side. It's good that you write this so you show the examiner that you got to the right hand side of p of k plus 1. By the way, I don't think I wrote tip number 5, so let me do that right now. Before I move to tip number 6, which is to vomit the conclusion. The conclusion is a sentence that can be applied to any induction proof if you vomit it the correct way. And this is the template that you should use. Given that p of 1 is true and p of k plus 1 is true whenever p of k is true, and the interval that we're talking about is all positive integers, so for some positive integer k, then by the principle of mathematical induction, p of n is true for all positive integers. Now, what changes in this conclusion from an exercise to exercise? Well, sometimes the induction proof does not start at 1. This is not the case. This one actually starts at 1, so there you have it. The interval might change, but the structure itself is pretty much the same. So these are the 6 tips for tackling induction proofs that involve series.